A lot of presentations have been happening today, so we know they're the last ones, so we'll try to get all you guys out here as quickly as possible, but I just want to show you everything that we did in the past year. Starts off, I'm Andre Rodriguez. I was essentially the project manager for this project, and I had to make sure everyone here was collaborating effectively and make sure we got to the end goal of our complete prosthetic.
I'm Lucas Rojas. I was in charge of testing our design.
I'm in Oakley. I was in charge of some of the designs and then client-side communications.
And then I'm Ben Jordan. I did a lot of the CAD work and then some simulations and some material research and that kind of thing.
So I'd like to start off with our objectives for this project. I'd like to start off with going over our problem statement, our scope, our requirements for this project, as well as our current test subject that we had for this project throughout the whole year. So essentially, our problem statement is that development of upper limb prosthetics are quite expensive. They can range all the way up between $1,000 up to $100,000. So we wanted to make a prosthetic that was able to somewhat mitigate that cost for the client. And then also complex control systems. The most complex control systems are usually going to be between myoelectric prosthetic devices, and those are the ones that measure synapses that happen in your muscles in your body. So we wanted a prosthetic that was able to achieve certain complex motions that a hand can do without that extreme complex design that goes into prosthetic device. We also wanted to lower the maintenance that's needed for prosthetic. So like I said, in those complex systems, a lot of it is a coordination with all the synapses that go on the body. So we wanted a prosthetic that requires you to just be able to put it on and it works. We wanted that to be as seamless as possible, as well as any maintenance that was required. Any parts that go missing or are damaged can easily be manufactured and put into place to be used within a couple hours. So our scope of work was essentially constricted to a transradial, which is a below elbow amputation. So this is a body power prosthetic, and I'll go into what exactly that is in a little bit. To ensure the prototype is capable of performing everyday tasks. Your hand and arm are big components of what you do on a daily basis. So you're grabbing, you're holding things, and a lot of that goes without thinking. But for an amputee who's using a prosthetic, you have to actually think about where your hands are and what you're actually grabbing. So we wanted that to be able to perform multiple daily tasks like holding something like this. We also want to produce a low-cost prosthetic. Like I said earlier, we wanted to mitigate the amount of cost it actually takes to have a prosthetic device. And perform component testing in accordance with application standards. Lucas here was our guy on requiring all the standards we need to adhere to and to actually test and make sure we were within constraints of those.
For prosthetic, we have sort of design requirements. Our first one being that we wanted our prosthetic arm to be able to hold 40 newtons of force. And we were thinking about what's the heaviest thing a person usually picks up in their day-to-day life. And we came to the conclusion that it was a jug of milk, which does weigh around 38 to 39 newtons. So that was our main objective. We also wanted to develop a lockable finger system that will allow the wearer to get a grip on something and then just keep it there without any further strain on their muscles. Because the way body power prosthetics works is in order to get any motion with it, you have to continuously use your back muscles in order to get to output on the system. The three grips we need are the cylindrical grip, which can be seen in the pictures, in which you use your thumb and your fingers to hold anything. The hook grip, in which you grab anything that has a handle grip. And then the pinch grip, in which you use your thumb and your index finger in order to hold smaller grips. Last thing, we want to get testing results that show that our design is accommodating to standards. We want an annual weight loss of less than 1% per year, and as well as a deflection loss of less than 5%, in order to have a design that doesn't need to get replaced every year or every couple of years.
This brings us to our test patient. Arnie Hartman unfortunately wasn't able to make it here today, but he is a below elbow amputee. He's had 50 years of experience. He previously used hook style prosthetics, which we'll go over what that means in a little bit, but he's used to body powered prosthetics. He's used those in the past. He provided valuable feedback to the team, and we'll go over that feedback as well, and that helped us in our iterative process. He also we also took measurements of a side of a sound arm, which is the non-affected side. Took measurements of that so that way we could design around the current conditions of a real prosthetic wearer. And then we took a 3D scan and a plaster mold of his arm or of his affected side so that way we can model the prosthetic around that to fit him.
Okay, now into the design, we're all gonna be going over the functions, and then some of the subsystems we have, including whipple tree, frame, thumb, fingers, block, and forearm. So what a body part prosthetic is a prosthetic that goes on the back and has no electrical components. It is all mechanical. It transfers the power from the motion from the back down through a cable, through a single input, into the actual hand to actually open and close it. So the three movements that are possible within a prosthetic user is going to be the scapular protraction, which is whenever you move your shoulders forward, the shoulder adduction whenever you move your shoulder away from your body, and elbow flexion whenever you pivot around from your elbow. Those are the three movements that a amputation with a transradial amputation is able to achieve. So some of our constraints are going to be the proper fit for our test subject's arm. We wanted it to be as geometrically congruent with both hands. We also wanted it that goes into corresponding with the test subject's sound arm. And then, as I mentioned earlier, we bi-powered. So we have one input. So this is from this main cable that connects all the way from the harness down to this single cable into the forearm. And we also wanted to consider weight. So weight is a big thing. We wanted it to make as closely to what actually a person's arm is, or less. Now this is the full final assembly we have here. The biggest components are going to be the forearm, the whipple tree, which is what is producing the movement between all our digits, the fingers, and the thumb. Now you may be confused as to what the whipple tree is. So here is a big exploded view of what we have here. So it's multiple pieces, which we'll go into later. And then we also have a smaller subsystem, which is going to be part of the locking device, which is actually in place in the forearm.
So I'll explain what a whipple tree mechanism is. Funny enough, it actually comes originally from horse-driven carriages. If you imagine you have a set of 4 horses on your carriage, and one of the horses is going faster or going slightly ahead, you still want all of that force to be distributed across all 4 horses to pull your carriage. That same concept was used in reverse here, whereas whenever you're pulling the fingers, you want to distribute the force across all 4 of them. One of the problems with typical or normal prosthetic users is if you just have one hand with one cable that pulls like a bar all at one time, is as soon as there's made contact with the object, it will not distribute the force, and so all of it will just be between the thumb and the fingers. And so the whipple tree was designed to essentially accommodate for that and to design around that. So you can see here different movements. This is just pulling it down. There's other variations as well, and we'll go into how that affects how the finger is pulled. But what's happening is one side can pivot, this side will close if this one is obstructed, and so forth. So also this is the whipple tree. I'm gonna go over really quickly. This is what we call the stage 1, and this is the stage 2. This is the slide that will slide along the whipple rail on the frame of the device. So what are some of the issues on the initial concept, the initial design as of the fall semester, was that there's some tolerancing issue, especially on this link right here and on these points. And the stage 2 was too complicated, and we'll get into that in a little bit. This is the final design. As you can see, we increased the diameter of these pegs to increase the rigidity and the strength of the whipple tree, as well as redesigned completely the stage 2 links. Here's the stage 2. This was the original design, and it was far too complicated. As you can see, there's 3 different sections here. For one, it was very small, and the printer was not able to print all these individual parts, and so we could not link the whole system together, which required a redesign. Additionally, these holes for the paracord were not able to be printed either out of 3D printed plastic, and so we had to redesign and account for that as well. And this is the final concept of the second stage 2 whipple. It is a print in place method, and it was designed to be more sturdy than the previous designs and account for some of those changes. As you can see, there's one hole here that crosses through the paracord, and we'll get into how that connects here in a little bit as well. This is just a diagram of how that is happening. So it's printed all at one time, which both increased the speed that we were able to manufacture these devices, and then also the strength of the device overall. This is the frame. This was the initial concept as a fall as well. Several issues were here and several things that we wound up not needing. For one of them though, we had to move the thumb slot backwards to allow for more space for the whippletree mechanism. That as well as changing some of just the overall look of it. There's some sharp edges on the original design, and we wanted to account for those in the final one. This right here is the final design. As you can see, we also removed this cantilever edge, added a cave on there, so that way the printer could print it at one time without supports, and that's the final design. This right here is for the thumb settings. We wanted a way to allow the thumb to have multiple different, or to be more versatile. And so we added different settings that require force to move it to opposition grip and then that cylindrical grip that we were talking about earlier. That way the thumb could oppose the rest of the fingers. That was done with a ball plunger, which is essentially a ball bearing attached to a spring and a metal housing. This was placed inside of the frame, and then the thumb was developed with indents, so that way whenever it was moved across the ball plunger, it would push in the ball, the sphere, the middle sphere, and then allow it to re-indent whenever the next setting was found.
Now I get into the finger design. Before I get into the design work of it though, I will briefly explain the anatomical language that we use throughout the process of designing these fingers. The initial part is the proximal, that's downstream of the knuckle. The proximal phalanx is what it's called, and it's connected to the rest of the hand by the MCP joint. Downstream again, then we have the medial phalanx. It is connected to the proximal through the PIP joint, and then your fingertip or the distal phalanx is connected to the medial through the DIP joint. We use this language to call our pieces. These pieces were designed to be anatomically externally similar to the shape of the human finger. And just as the human finger has barriers, physical barriers with the cartilage in your finger, your ligaments in your finger to prevent for hyperextension. We also had a physical barrier to prevent for hyperextension. The retention peg was made a simple rectangle. The retention peg is used for our silicone fingertips. We wanted to simulate the elasticity of our fingertips, and so by using silicone and putting a retention peg into the silicone, we could have the silicone cure around the retention peg, and then place the silicone on the distal end of the finger. Here's our final concept of our fingers. You can see we shortened down the length of each of the fingers and each individual part. Right here you can see that we have holes coming out the bottom now. These are 90-degree curved channels to prevent cord binding and to allow for our actual actuation of the finger that we intended. Initially we had the cord routing all the way through and then back into the frame. This was found to be counterproductive and provided more binding of the finger and didn't allow for the retraction. And the finger the retention peg was optimized so that we could have more of a grip on that silicone. It was shaped into an arrowhead style of piece and then placed into the distal end. To reiterate what Lucas brought up at the beginning, we have the lock to form a grip and hold that grip without any extra use from the user. So the user, let's say they want to pick up something by protracting their scapula. They will protract their scapula, it will pull on the cable, and it will wind the barrel so that the barrel rotates and puts the locking paw right here into a position on the teeth of the barrel where it will allow for no more rotation of the barrel once the user lets go of tension. This will hold the grip that they intend to use until they pull more on the cable and the locking paw goes back to its horizontal position. Once the user lets go of any tension through the cable, when it is in that horizontal position, the torsion spring allows for rotation back to its resting state right here. As you can see in the unprimed hull, it will not catch into the teeth of the barrel. Here is our initial concept for a locking mechanism. We used a very simple placeholder bracket in the initial design because we did not intend, or we did not know where we intended to place the locking mechanism. Here we have a small locking pawl. This was later changed in our current iteration to provide a greater force angle upon the teeth of the barrel. And the torsion spring was initially a metal spring from a drill press that was found to be too stiff and to be too big for our purposes. And so in our final concept, we were able to 3D print our own torsion spring and design around the stiffness that we wanted to have for our torsion spring. And by designing it, we were able to place it within the locking barrel to our size specifications. The locking mechanism was placed into the forearm cavity, as previously stated, and to design around that, since the forearm is a very conical shape, we wanted to have the locking mechanism bracket be shaped into, to be meshed correctly and to the contour of the forearm. The pawl arm, as stated before, was too short, and so we had to size down where the diameter where the teeth protrude from, and then we were able to lengthen the pawl to create a greater force angle. And now I'll give it over to Jay to explain the form.
So this is the original concept we had for the final forearm during the previous design semester. It is pretty close to the shape of an actual human arm. The only things that we had to change this most recent semester was the fact that right in here is actually a solid piece of plastic, and then we originally thought that would allow for more structural integrity to the prosthetic. However, we needed to change that because of our original placement for our lock, and we also realized that it's actually over-designed. You don't need that place today in that. There's also these holes as well for Velcro straps that are currently on here. Now, that allows for this to be tightened to actually increase the tolerance that is decrease the tolerance for the prosthetic to actually be in place. That way, in case there's any swelling or any geometrical changes to the amputee's affected side, that you can still use this device up to a certain point. And then, now we actually have this final prosthetic device here. So the only changes that happened in this past semester were the placement of the lock. So it's actually in place in here within the actual arm with this bracket that goes in place here, as well as properly placed. Okay. I swear it goes back into place. I had it reversed. There we go. Okay, there's also cable guides here to keep this Bowden cable in place. That way this cable is actually free to maintain. And then this cable goes all the way through here, comes out the end, and there's that. And to turn all the digits into place. Now I will be going over the cost breakdown for our prosthetic. Thank you. So like I said earlier, one of our biggest things was decreasing the cost it actually takes to actually manufacture and give a prosthetic to a client who actually needs it. So this is the total cost it took for all of the materials we had. This includes all the prices you see, all the materials you see here, as well as the current ones we have as waste. So you end up with a total cost of $1,057.71. The biggest component for all these big prices is going to be the prosthetic liner, the harness, as well as the amount of actual plastic material they've actually purchased, which is actually going to be put into the waste. But to actually produce one complete prosthetic that you see here, it only costs $435. However, that still includes the prosthetic liner, which costs $270, as well as the harness, which costs $85. So this harness right here, you're not able to produce in-house, and then the prosthetic liner, which is actually in storage right now. I was meant to bring it here to actually show you what it looks like. But if a person would actually that already have those in place and then we're able to produce this product themselves, it would actually only cost $30.11, which actually get much decrease, which actually lowers the cost by quite a big margin. Now we going into manufacturing, which includes the molding of the silicone fingertips as well as the assembly of the product.
So here we have our silicone mold casing. We use this to design our fingertips to the shape that we wanted it to be. Since using silicone, we had to let it cure for a time. The silicone fingertips were designed, again, to be elastic and bring more friction to our grip. Originally, syringes were used to input precise amounts of silicone testing material into the silicone molds. Eventually, we switched over to a all-purpose silicone from a caulking gun, and we were able to pipe it straight into the silicone molding cast. This is the initial run of our silicone mold. You can see that the silicone itself picked up a lot of particulates. This was an initial testing. The all-purpose silicone that we use right now, it does not pick up particulates just as much. The assembly, the main portions of our assembly was using raw filament material and using a lighter to heat up the end of the filament edge and pushing it into a nodule piece to then allow for the joints to be held in place without the fingers falling apart. Super glue was used in the retention pegs to permanently fix the silicone fingertips onto the distal end of the finger. And the locking mechanism barrel, it was printed in two parts, and we used super glue to affix those two barrels to make it one cohesive piece. And I'll give it over to testing.
And so for our design, we tested our arms, safety testing and strength testing to determine in which state our arm will be in potentially a year or two from now, not to determine that we do meet our requirement of 14 newtons of force. So for our safety testing, we did a periodic linear actuator test. It cannot be seen on the picture, but right off camera, there's a linear actuator that will pull and relax the finger for a simulated 2 weeks of use. Now, the way these tests are usually done is they simulate 2 weeks of use, and then they extrapolate the numbers they get from the test to figure out how is the arm going to look like in 1 year or two from now. Our test was performed 3 times over several days, and the way we determine where is through weight testing. We weight the fingers before and after the test, and also we take pictures with the same level and same camera angle before and after the test in order to both determine the loss in weight as a percentage and the loss in actuation as a percentage. And our passing criteria is to have less than 1% of annual weight loss and less than 5% in deflection loss. So after conducting the test, our fingers showed an average weight loss of about 0.0025%, which if you multiply that by 4 to account for all the fingers and then multiply that further to account for a year of use, we end up with a figure of only 0.365% of annual weight loss, which does fall below the 1% requirement that we wanted. That's from the data in the top of the table. And then the bottom of the table is the angles before and after the test was performed. We saw a loss on the distal interphalangeal joint, loss the IP joint, of only 4.65%, and a loss of 3.8% on the PIT joint, which is the proximal interphalangeal joint, which both fall below 5%, meaning that we successfully made a product that should last the user a year or two without any issue. For strength testing, we ended up going with a simple test of just using volumetric equipment to measure weight in a bucket and just have the arm hold the bucket. And we increased the weight at a rate of 1 to 10 newtons per second by adding water, which using the volumetric equipment, we knew how much we were adding, so we could figure out how much weight the arm is handling before it breaks. So our passing criteria again was 40 newtons, and we recorded every time we had either a slip or a catastrophic failure, which we did have a catastrophic failure at 73.23 newtons, which is almost double what we wanted, as well as we had additional slips at 68.6 newtons and 79.5 newtons. As you can see, our failure occurred on the Whipple, which is probably the best case scenario since a new Whipple can be reprinted within only 1 hour or 2. So next we want to go into a demonstration to show Arnie using the prosthetic arm.
Yes. So here we took a video of actually him achieving all the grips that we were required to achieve. So right here, first we have the pinch grip. So here he's picking up a small bottle lid between the the index and the middle finger as well as the thumb. This achieves that single pinch grip, and then as you can also see, he's just holding it like this. And then next we have the cylindrical grip. So here he's actually going to be picking up a red box to achieve this single grip where you still have your finger, still have your thumb engaged. Yes. And finally, we have the hook grip. So the hook grip was the thumb on the outside of the grip. Here, he's actually holding a briefcase, but this briefcase also actually has 10 pounds in it, and he's holding it below his waist. So him in person is still able to hold up 10 pounds without it breaking, or him actually giving us feedback on him having too much stress on his shoulder. So we've achieved all of our required grips, as well as being able to actually, you see in person, he's able to hold up 10 pounds. Now, as for conclusions, we're going to give you some challenges that we had throughout this project, as well as our recommendations for continued work on this project, and some accomplishments that we were able to achieve.
So some challenges that we faced throughout this design project was that the lock in its current formation is not able to functionally work for our project. It was designed to have a full 360 degrees of rotation, but it failed in that regard due to too wide of a diameter around the cable, and it provided insufficient rotation at only a few degrees. We had a parts delay early in the spring semester that put us just a bit behind our design. And we also had the department's tensile testing machine was not fully functional, and we could not perform proper materials testing. We had an inconsistent assembly, and this is mainly due to our paracord and the knots that we tied around our paracord. It provided inconsistent length of our fingers, and a tighter tied paracord would provide more rotation to a loose tied knot that would provide only a little bit, and so often we would have our fingers out of line due to the assembly. And then we missed some testing procedures.
Yeah, there are additional tests we were supposed to conduct. For example, the pinch grip test would determine how much force the thumb and the index can handle before they let go of an object. But due to a misalignment with both our thumb and our index, that can be seen there, we could not conduct this test. There was also cyclic tests that should have been performed on the lock itself, but since the lock didn't work, we didn't get to do any testing on that.
I'll pass it over to Ben for some recommendations.
Yeah, so for our recommendations, one of the first ones is obviously to get the locking mechanism working. Some of the proposed ways that we could do that would be to decrease the diameter of the locking ball, or of the locking wheel or the barrel, which would would increase more rotational. Additionally, the thumb could be further improved. Some of the feedback we got from Arnie was that the thumb was stationary and also had no silicone gripping. And so one of the proposed solutions to that would be to break it up into 2 parts and allow for the thumb to have some deflection to more to better fit an object or a cylinder or something like that. Additionally, not on this, but also one of the problems we had with the assembly was that the cables were all routed differently, and so some better way of affixing the cables to the whippletree mechanism and the cable to the rest of the body would have been very ideal in this case.
Okay. So then, I'd like to go over the accomplishments we received. So like I said earlier, the high cost is actually one of the big components of this. So like I said earlier, prosthetic devices can range between $5,000 to $100,000. However, to make one of these products by itself, it only costs $435. However, these numbers are slightly skewed because these numbers are likely to include labor. However, this is only materials cost. So this price would go up if you were to actually mass produce this and give it to multiple people. So this price would fluctuate slightly higher, but only materials cost and only platform is very comfortable. Now, as complex control systems, all four fingers are able to articulate and achieve those 3 grips as I saw it earlier. So all I have to do is pull it on this one cable, and the fingers are able to actually articulate by themselves through this swivel tree here. Now, for the need maintenance, the overload causes the swivel tree to break, and the cable needs to be replaced and assembled quickly. So, as we saw earlier during the spring testing, the parts that actually failed were the swivel tree inside, and then that's a small piece that is able, like Lucas said earlier, that would be produced in less than 1 hour if you were to 3D print it again. I would like to give some special thanks to all the people who helped us throughout this year. We had Arnie Hartman, who was our test subject, who put up with all the things that we put him through. Winnie Brandon, who was our representative for West Texas Rehab Center, she helped us out primarily learning actually how to choose this design because this is the one that actually people are going to use most is through body power prosthetics. And then Kendra Nix, who was our physical therapist advisor, helped us realize certain things that actually go on through the patient side. Says as we are not amputees, we actually don't know certain things, and she helped us a lot in that regard. Mike Brash was our academic advisor throughout this whole year, actually make sure that we were actually staying on task throughout the whole semester, and then push us to actually achieve certain things. Olivia Castro, who made sure we actually purchased all of our materials actually and in time, and then helped us through that initial parts delay, like I said, like we mentioned earlier. Leo Gravely, who helped us actually certain things in manufacturing. We had actually we were able to go and ask him questions, make sure, and then he was able to give us feedback and actually figure out certain ways we could change it, and then also give us insight actually pursue better ways to actually produce it. And then all of our peers who gave us feedback throughout the whole year, gave us certain recommendations that allowed us to actually move forward with the project and then help get everything lively. Thank you guys so much for being here. We'd like to open up for questions.
What caused you to think about doing this particular project?
It was kind of a passion project of mine that Mr. Bratchford reached out over the summer, and he was asking whether or not we had any projects that we wanted to bring to the table. I wanted to get into biomechanical engineering, eventually biomedical engineering in my future, and so I brought this up, and we reached out to West Texas Rehab and the physical therapy here and worked with them closely in creating this project.
Essentially, we just proposed it. Bradford said we could do it, so we decided this project would be both different from everything that we've ever done, and then different from other capstones. None of them have been able to, or have, that we've noticed, gone into actually personalized biomechanicals. We thought that'd be a different challenge for us, and I like to say we enjoyed it quite a lot. It was, like I said, very different from other projects we've done in class and from other capstones.
Did you use any of the ideas that are already in the market to help create this?
Yeah, so one of the primary things is the reason there's obviously electronical bionic arms that they sell. Those are the ones that are expensive. Those are the ones that cost a lot to repair. And so the market mostly uses, if you're an actual prosthetic wearer, most of the time you're going to use a body powered prosthetic. A lot of them are hook, that kind of grip that you saw in the very beginning. That hook grip allows for one action, and we wanted to somehow bridge the gap between those bionicle arms and those just simple hook grips. And so this was our attempt at that. So in terms of what we use from the market, pretty much all the research for how these things work, how to do the testing, was from the research or the market standards.
Basically finding an in-between between the novelty of a bionic arm or a fully functioning retraction arm and the functionality of a body-powered prosthetic.
What is original and unique about y'all's design compared to those in the industry?
So we did use that swivel tree mechanism. It has been done at other times, but in conjunction with a locking mechanism. We hadn't seen that in the market in the research that we did.
The biggest thing is like a lot of them don't allow for that locking, so that was the biggest challenge, and we actually wanted to achieve that. But it's harder than it looks. So we wanted to achieve both the individual movements of the fingers as well as being able to lock in place. That was a part of the novelty because those are all being done separately. We wanted to bridge the gap and put those all together in one actual system.
How does it compare your 400 design with the cheapest one that is 5,000 in terms of functionality?
It compares, in functionality, we were able to achieve all of our goals. It's probably not ready for market.
No,
work
definitely
right now.
prototype.
It's definitely a prototype
We
still.
will not be legally
But-
allowed to distribute this. We're not.
But for our purposes and achieving our goals, it compared pretty well.
But I mean, is like, what kind of functionality does the $5,000 have that yours doesn't have?
So the least expensive body powered one, typically what functionalities would they have compared to yours?
Well, usually they'll just have the hook grip. I would suppose that, it is the very basic one cable to separate, two hooks that can then pinch around an object or hook up and carry an object. And that's a very basic kind of prosthetic. Ours is a bit more novel, that it has finger retraction and that we have that locking grip, so
Hmm.
that'll be the difference.
So I know this was a year-long project, but let's say because y'all were trying to make it to where anybody could put it together themselves, if I had all the correct materials, had all the 3D printer and everything that I needed to construct it, roughly how long would it take for me to build it? I know it's like a very in-depth question.
Yeah,
but-
I think the total.
Like if you were to print everything from zero and then have it fully functional, how long would it take you to like assemble it
Mhm.
and produce it for yourself?
Yes, if I had everything.
Yeah, if I had, I'd say,
The print time alone takes maybe like 4 days, yeah, to print pieces.
that's if you're going from all 24 hours. I'd say 2 weeks, 2 weeks to fully print it, fully assemble it yourself, and then make sure everything's properly assembled.
Hmm.
Just to give you time. I don't want to give you a wrong answer, but ballpark, you can get it done within 2 weeks if you were to just print it from our archive files we had.
If you have all the pieces printed though, like beforehand, and like we're able to buy these pieces outside stores, then if the assembly itself could only take like maybe a day or so.
Yes, in the back.
So, a lot of, I saw your tests, most of them were from like kind of a dead hang, position where there's not an acceleration being imposed on whatever force it is. So, I know you said that your goal was 40 newtons, right? That was your minimum that you wanted to hit. But if the tests are being imposed, like being performed at kind of a dead hang, you're not simulating that acceleration that would be used, like when you're picking up a jug of milk, you're not just hanging it, right? You're moving it. It's that importance,
Yeah.
more force on it, right? So do you foresee that everyday acceleration adding potentially more wear and tear to this, or do you see that being an issue, or because you hit 78 newtons, do you think that is enough to compensate for that, like everyday acceleration? Does that make sense?
Yeah, it does. I mean, I would say the figures we got would be sufficient. During testing, we were trying our best to keep the load consistent, but due to some issues, that was not really possible to us. So it's not like it's purely stationary either. So we believe it should be more than possible to carry the jug of milk even with the additional acceleration.
We can't give you like a quantitative number because we did not test it for that. We wanted to eliminate as many factors as possible, so just having it in that dead hang seemed like the most advisable. But for the testing to do that, we'd actually be able to achieve, see it at the needed amount of force that we need to exert to actually overcome that.
Yeah, I would point out that getting in lots of engineering projects, one of the hardest things to do is figure out what are the design loads. You know, that's basically what this discussion is about. What should the design load be? That's actually one of the harder problems to figure out.
One of the things that we also tested, we did some simulations over it, was just the cantilever of applying weight just perpendicular to the rest of the finger. And that's an area that actually could be improved based off of our simulation findings. Particularly the faults were at those filament connections. And so those probably for some more real live use would need to be changed for some stronger material. And so we did some simulations of that sort of thing, and I'm sure that that's where we could kind of pull in some of that acceleration data, and as well just doing some testing, you know, of that particular area, because it's a dynamic environment. These fingers, like the hand picks up, like you don't even think about all the different movements you're doing throughout the day. So testing for all of those is just kind of out of our scope this time.
And since the other point was at the Whipple, beefing up the Whipple or choosing a different material might allow for greater force to be applied to the bar.
Hey, so that just brings up two, second question I have. The first question I had was, you showed some, standards, well, some design goals in terms of fatigue, in terms of loss of angular motion, and where did those come from?
That's from the international, the ISO, International Society for Standardization.
It'd be nice to know where you got that standard from.
Yeah,
when you're
sorry.
talking about it. And so but the second question, which you just reminded me of, is, so when you exceeded the load capacity in the grip, you had a catastrophic failure, right? Have you thought about how you can redesign this so when you exceed the capacities, you don't have catastrophic failures, and maybe all you do is drop the jug of milk? Or something, right?
Right, something else breaks first.
Yeah, or yields in a fashion that's not catastrophic.
No, that's certainly like great feedback.
Just, you know, we civil engineers, in terms of buildings, like, you know, we design buildings so in earthquakes that they don't collapse, right? That they just they fail,
Yeah.
but they don't collapse, and people don't die inside. So I mean, this is not that critical, but
Just dropping something on your foot.
well, I mean, you can design it so that when you're exceeding the structural capacity of any part, something happens so that you don't actually catastrophically fail the mechanism and then have to fix it, right?
Going into that, I figured at least we figured that you don't want it to bend because at least the user wouldn't know what broke. So it kind of helps that you.
Yeah, there's that too, yeah.
Because if you know where it broke at the Whipple, so you have to replace the Whipple.
Yeah.
You're not having to go in there and figure out which parts broke.
No. We've been civil engineering, we have an analogous thing where when we attach the foundation, columns to the foundations in seismic areas, we designed it so if there's a failure, it's in a place where we know it's failed and it's not failed below the ground, so that we don't know that, and we think, hey, everything's fine, and it's not, so that's a good point. Yeah. You wanna know where the failure is so you can fix it.
Yes.
Yeah, or you know that it's a failure.
I don't know much about 3D printing because you did everything 3D printing, right?
Correct.
Yes.
Can you have a kind of, I'm thinking in the mechanism that failed, because you mentioned one possible solution is change the material, right?
So it's either change the material or the infill that the 3D printer is doing, is printing at. I think that example was at like 30%, and that number could be boosted. It's a weight issue at that point, but for
Okay.
example, it's probably negative.
So that was my other question. Can you change if it's, either the topology of the mechanism or the shape of the mechanism, or the other thing, that for sure could be possible with the 3D printing.
Yeah.
But my question was probably a reinforcement, can you be able to have a piece of metal that reinforces the 3D printing?
I think one of the best outcomes or fixes that could be done would be to replace a lot of the plastic pin connections with metal connections like that, so that way they can yield, they can bend. And there's actually some solutions that you can find that you can insert the metal into the plastic while it's printing, have it finish, and then it encases it. And that'd probably be one of the better solutions for
That
our
just
case.
means going from stage 1 to stage 2, right?
Right, yeah, stage 1 to stage 2, and then even within the fingers.
If you had other manufacturing methodologies at your disposal, would you design with those materials in mind? Like, would those be natural swap outs to just standard ABS?
One thing with the whole cowl setup, one of the thoughts that we were having at the beginning semester is to reduce the weight of the entire assembly, is to actually have it be carbon fiber wrapped. Right now, that's kind of out of, our idea is to make it work. The carbon fiber, you can even find some of those examples online if you purchase those. Those increase the strength and reduce the weight.
Can you go to the slide when you have you have an initial design for the casing, I don't know how you call the casing.
Full assembly?
That one, and then the next one. Okay, so I see something in the previous one, that is the slots are like rounded,
Yes.
and in the next one, they are like a square.
Yes.
Why?
That was due to, first, the oval shapes were too slender, so it was printing incorrectly. So I increased those and then made them squares because the actual Velcro is just a square. And I thought that'd just be an easy shape to print. And then I increased the size of it because the printer wasn't printing it correctly, and then it also allows it to be moved in case it's like, it's in the
Really?
way.
So that's for the straps, okay. I thought it was different functionality, I thought it was just that being able to be more flexible when you put it in again.
Yes, yes, it is more flexible here, and then it can be Velcro strapped.
Hopefully that's
to-
tight
to-
around.
Yes.
Also, we added this little notch in the middle for stress concentration.
Ah, that's nice.
Yeah. I was gonna ask you about stress concentrate. Did you do even, without even doing a finite element analysis, did you look at where the Whipple failed? Did you look at the print? I saw a lot of discontinuities in the print.
It was-
Yeah, yeah.
It's
Or
really
quick,
difficult to
whatever you wanna
identify.
call them, quick geometry changes. So did you even look for a qualitative stress concentration analysis to figure out how to redesign that?
So we looked at different materials, and this is kind of one of my goals was to do the material testing on the lab pixometer, is to actually get those values so we could perform those kind of tests.
Uh-huh.
One of the problems with 3D printers is that there's a lot, like you're saying, of inconsistencies, a lot of defects within the material.
Yeah, with the anisotropic for one thing, right?
Right,
Across
and
the
they're laid
anisotropic.
across each other, so if
Right.
you're putting shear on the direction it's printed,
Right.
wherever you get the direction it's printed, then it will just shear off. And so we wanted to do the material testing so we could get those numbers, so we could have accurate calculations.
Right.
Otherwise, we're relying on research that's on just the standard materials, like the actual PLA
Yeah,
plastic.
it's isotropic when it's not, right?
Right, and so we didn't want to do those calculations, but for us, the best thing to do was just to increase its breaking, make it larger, increase the infill, that sort of thing.
How did you select the size and shape of the hand and the fingers and things? Did y'all take that into account?
Those are all based off of actually, of Arnie's, physical measurements. We took measurements of his sound arm. So the geometry of the forearm is to his arm, and then the size of the fingers and the palm are as well.
Did you have to learn how to do that?
We had some.
Did
coaching
like
from-
somebody from physiology or something have to explain to you
Yeah,
how
we
to
got
make
a
those
sheet
measurements?
that told us exactly what measurements we need to take and how to take it.
Yes.
I don't
That was
Mr.
Brandon's
Brandon,
next, right?
Mr. Brandon sent us some, like images to, where the condyles were so that we could measure from condyle to point of interest and measure accordingly on
Cool.
Arnie's arm. Yes.
Did Arnie have any feedback on the difficulty of putting it on or using it? Or
No,
how it
that
compares?
Not putting on.
That was something we asked, every time.
And he was comfortable with it. Putting it on was very easy for him. He was able to actually just strap it over like a backpack. The only issues that he had was mainly the thumb, that it wasn't able to fully extend on some certain objects. And that, what else? Like the fingers didn't track.
The pinch grip wasn't as he expected, because
Yeah.
he was under the impression that like it would model the way that a hand does, but there's too many degrees of freedom in the thumb, first of all, as well as other fingers. So achieving certain grips are harder because it has to go in one linear action. So in his interpretation, he was like, oh, this is a hand, so it should be able to grab it like this, but it doesn't work like that. So we had to treat it as if you were doing it with the original claw grip, which he was able to pick up that bottle plate as we were showing earlier. So there's a learning curve to it, but with all prosthetics. We just didn't have enough time with actually him wearing it like day in, day out, to get feedback for an extended period of time. It was just in hour increments over a month.
But with those changes in mind, does he see like potential for this to be a good prosthetic for like maybe people who can afford the better ones?
Yeah, he really liked being able to wear it. He was like, oh, this is really cool. He himself was messing with the thumb while we were either making changes to it or having to gather certain materials, something like that. So he would be messing around with it. So he found enjoyment out of it at least. But he really liked it, mostly from the fact that he has a claw, a metal claw that he used previously. However, in social situations, he was scared of it actually hurting someone. So he liked the fact that one, it's made all out of plastic and has fingers that actually move depending on if they're hit. So there's no chance of it, at least in
Smacking,
yeah.
On the most distal. And so like, one of the things that you don't realize as, if you don't have a prosthetic or if you're not amputee, is that you have a situational awareness of where your hands are, where your fingers are at any time. Whenever you lose that awareness of where those things are. So what he was scared about is when he had young kids, this is 50 years ago for him, is he'd be walking around, one of his kids would be at this height, and he doesn't know where that end of that claw is, and so he was concerned about that, so that's why he discontinued his use, and he found a way to live life without his hand, and does just fine, so.
You guys learned some stuff about legal aspects of medical devices. You wanna talk about that for a second?
Yes, this is considered a medical device because it is treating a person's condition. We are not licensed professionals, so we can't give it to him. But if we were to make all the files we had open source and he was able to add them somewhere else and print them out himself and assemble it himself, he'd be able to use it without having to go through the medical channels there.
But he would take on the risk instead of us.
Legally, I cannot recommend that because people in this room may not agree with that, but it is an option.
But no, that's a very good option. My question was related, what's the future of this? Because I think that would be great, so, like, really, really great.
Having it open source would be a great opportunity for then other people. There's already some open source 3D printable prosthetic arms on the market right now. People can go in and do that. It's Andre Dukek or something. He's Russian and he has his own whole arm that's open source, and you can become a maker of that. But yeah, creating.
But his is the claw, are you saying?
He uses a arm cable pulling, has flexion of the fingers. His cable pulling pulls it apart, and so it's different from his in that aspect. And he only has 3 fingers on his. It's similar to the claw in that as well.
Is the Whipple the innovation for you guys?
The Whipple, yeah, Whipple's kind of novel for us.
In combination with the lock. That's the novelty part, is trying to incorporate those 2 parts together instead of separately.
An example of the Whipple that we got the arm from was just a hand prosthetic where it applies whenever you tilt your wrist, it will then retract the fingers from the hand. But we have the whole arm, and so we had to come up with different ways of putting that input to retract the fingers.
Making it open source, would you change the dimensions from not Arnie to something more average?
See, that's the hard part, is because you want it to be form fitted to your placement, especially because amputations can happen all the way throughout this whole arm. So whether you lose your hand here, or here, and potentially even crayons, I forget the location above the elbow. So it's kind of hard in that aspect because it's made for him specifically. But anywhere from the wrist coupler down, you can make and have that fit. It just won't have perfect geometry with your hands. But if that's an issue, those files can totally be edited. And then it also helps that you also have the framework, and you can just make adjustments depending on if certain things aren't properly to fit for you.
There'd be a real
parametric.
Yeah, I was thinking
there's a real ability for this to be where you have certain dimensions that you take of the affected side and then of the sound side, and then you somehow, with the CAD workflow, write some sort of a script that would then assign all these different geometry values into the hand, which would then create your final version. Obviously, it'd have to be within some sort of range of, sizes, but that could definitely be done. It's just not something that we were foresighted enough in this design to do that. That'd probably have to be a full redesign of the entire assembly with that in mind, that parametric geometry in mind, in order to continue that kind of use. But that's definitely a thing that I was thinking about the thumb, I had to redesign it, but I made the CAD workflow so that way it could be parameterized and changed very quickly. So we would try to do that for the whole rest of the part.
Yeah, and you can probably use FreeCAD to parameterize that, which is also an open source.
With some sort of Python scripting,
Yeah.
and some sort of UI interface that could stream through to that, yeah. So, are we wrapping up? Is it
Best,
time?
yep, so last questions.
Yeah.
Top thing each one of you learned.
So some of the things that I learned from this project was it wasn't enough to just go into CAD and start working on something. I found that the old saying of working slow is working fast, and sometimes working fast winds up working slow. And so what I found is if I would have sat down and really considered the problems, really written out a solution, and really just tossed it around in my brain, I could have come up with better CAD models, better CAD designs that would have worked further, would have needed less iteration, and would have lasted longer into the project and potentially been better solutions had I done that. What I found myself doing though was there's a problem, I would hop in there and I would start designing without really thinking about the whole situation. So that's something I definitely learned from this project.
Very similar to Ben, I also had the same sort of design mindset where I would just jump in and start working on projects without formally actually writing out my steps. I also learned a lot more about tolerances with 3D printing that developed my skills with CAD and working with tolerances and all that. I learned how to really communicate myself to clients and to these guys, and I really appreciated just all the work I was able to do with these guys.
I said earlier, I was essentially the leader for this group. I've not had a project where it was over the span of greater than 3 months, so that was a big change. My biggest takeaway is that I led this project really free form, because it was like essentially a very creative project because we had open for many things like, hey, just make this arm fit to this guy and then have it work. So there wasn't as many constraints as there were for other projects, so I let it really free form, just as creative as possible. If you have an idea, go with it, see where it goes from there. But that lended it up to us having to reconsider certain things, so a lot of that was delaying us in certain aspects. So I think the biggest thing for me is like learning how to apply more rigidity to the way that the project is led. So I'd like to implement that in further projects that I actually do. Is like it may be a creative idea, but it's not further progressing us to the end of the goal. So just nix it and get rid of it and go on the next one.
As we said, time management.
One of my favorite lessons for everybody learning this.
So we just needed to think things through more. I was the testing guy, so for like a week or two towards the end, I was just sitting on the bench waiting for the design to be finished so testing could begin. And I wish I could have pushed myself out of my comfort zone more, because other than some electrical stuff for testing and some help on manufacturing, I feel like I could have done a lot more, especially during the design stage. So I wish, that's certainly something that would carry onto future projects for me. So I will hopefully do that.
Thank you very much, and commend you for pursuing a project that was interesting to you and unique. So thank you all very much.
If y'all want to come look at it, y'all are more than welcome to.